Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to module 5. In lecture 3, we are going to cover following concepts: introduction, then we will be having an overview of reflection seismology, under which we will be talking about travel time curves for reflection events. We will also see relation between travel time and ray path. We will also see travel time curves for multiple layers. Then finally, we will be talking about Dix equation. So in the previous lectures of module 5, we learnt about refraction seismology, which can be used to infer velocity and density variations, or you can say the elastic properties variations at several depths of the Earth. In reflection seismology, we are going to use the reflection data in order to infer the velocity variations within the several depths of the crust. So it can be used to find out the resources that might be available in terms of the mineralogical resources, oil resources, or the gas resources for the crust itself. So reflection seismology is considered to be very essential in oil and gas exploration, and its abundant use in oil and gas exploration has led to develop several techniques in the field of data acquisition and processing methods by the reflection seismologist. In order to understand what reflection seismology is, let's take a very simple example of one layer Earth, where you can see there is this layer which is having the velocity v0, under which there is an higher velocity layer of v1, that is basically a half space. And if you remember this diagram, we have seen in our previous lectures as well, where we have seen there was a source on the top of the surface and the receiver at the surface having the offset distance x, keeping the origin at the source. And when the source is excited, then it can basically produce three kinds of waves. One is the direct wave, another one is the reflected wave, and the third one is the head wave. We talked about the direct wave and the head wave in a very extensive manner in our previous lecture. But today, since we are talking about the reflection data, or you can say the reflection seismology, so we will be talking about our third ray, that is reflected wave, that is represented by this green color. So you can keep in the nutshell that the study associated with the reflected wave in order to infer the velocity and density variations within the crust is known as reflection seismology. So the travel time curve as a function of source to receiver distance is known as offset in reflection seismology. And if you remember, we have seen this equation, Tx square is equal to x square by v naught square plus 4 h naught square by v naught square. So this particular equation came from this particular triangle over here, and then we used the Pythagorean theorem in order to find the travel time of the reflected wave. So the travel time of the reflected wave, it is the total travel time of including the downgoing wave and also the upgoing wave after having its reflection at the interface over here. So if we rearrange this equation, we can write that Tx square minus x square minus v naught square is equal to t naught square. So this t naught square is the two-way travel time when the offset distance is 0, which means that source and receivers are located at the same point, just above the point of reflection. Now, if you look at this equation of reflection travel time, that is t as a function of offset square is equal to x square by v naught square plus t naught square. this particular equation is the equation of hyperbola. If we keep x is equal to 0 for the 0 offset distance, then you will find that you will remain with t square is equal to t naught square. And t naught is nothing but is a two-way travel time if the 0 offset is there. That means if you want to calculate T naught, then you can take just the two-way travel distance, that means the 2 of the thickness of the layer, that is H naught, that is divided by V naught, then T naught will be equal to 2 into H naught by V naught, and it is also known as two-way vertical time. And two-way vertical time is corresponding to the ray traveling vertically down to the reflector and back. Now, if you look at this particular diagram where we have kept the distance on the top, where the distance is increasing from left to right, and its distance is also known as offset distance, that means the distance between source and the receiver. So, and the y-axis is basically representing the two-way travel time for the ray of reflection between source and the receiver. And we have kept the time that is increasing downward. Why? Because we want to see the reflectors that is having the deeper depth from the top of the surface. So it will basically be correlate well with the data that we have in the real earth situation. So basically, in case if we have the 0 at the top and the time is increasing downward, then we can correlate it well with the different interfaces that we will encounter with in case of the real earth data. And there is one more reason to keep it as a time increasing downward is because we want to have our reflection hyperbola clearly visible as you go deeper down. And as you go deeper down, since the velocities are increasing, then the hyperbola will become flatter and flatter as you go deeper down the earth. Now, what about the hyperbola? So basically, the layer velocity can be found from the slope of the hyperbola. If you remember, we talked about the travel time curves, and in travel time curves, we said that if you can calculate the slope of the travel time curve, then it will give you the ray parameter. We will talk about the ray parameter shortly, and let's read it down. Layer velocity is found from the slope of the hyperbola because the slope decreases with increasing velocity. Flatter travel time curves indicate higher velocities. So you can see the reflection hyperbola at a depth coming from the interface that is having the shallower depth is having the slope higher, or you can say it is having more inclination, higher slope than the hyperbola that is coming from the deeper interface that is having the flatter response. In case if you go even deeper, then the hyperbola will become flatter and flatter if you go deeper down the earth. So the travel time equation can be written tx square is equal to x square by v naught square plus t naught square. If you compare it with the equation of line, that means y is equal to mx plus c, then it may give you that c is equal to t naught square, y is equal to tx square, and m is basically the slope, that is 1 by v naught square, and x is x square. So in case if you are going to make your travel time curve with respect to tx square and x square, that is the offset, then it should come the straight line, and the slope of the straight line will give you the velocity in the first layer. Now, what is normal move out? If you look at your data that we are talking about, the reflection data, that is nothing but the hyperbola. Let's make a diagram here. Here you have the offset x, and here you have a two-way travel time that is increasing downward. And if you look at your hyperbola, that may be something like this. And each of the point of the reflection hyperbola is representing towards the reflection event that might be coming from a point at the interface. So let's suppose this is your surface here, and on the top of the surface you have the source, and there you have a receiver, and this is your interface. First you excited the source, and it will basically go down, the ray will go down, reflect back from the reflector, and then will be recorded at the receiver. Now, if you will increase the distance between the source and the receiver, or you can say keep the distance variable at several points, then it may be something like this. And because it is traveling the longer path in the layer, so it will be recorded later. That means the total travel time for the second thing will be larger than the previous one. Subsequently, you can do it for the multiple offsets, and then what you will get your reflection events something like this. This is for low, this is for the offset that is smaller, and as you keep on increasing the offset, your reflection events will have the larger travel times. So something like this. So basically, in order to have the better signal to noise ratio, or you can say if you want to improve the quality of the reflection data, then you will have to perform this processing step in your data, that is known as normal move out. And this normal move out, you are basically doing something like you are making your hyperbola as a flat event, so that when you stack them together will lead to a higher value of the signal to noise ratio. So basically what you are going to do, you want to make this particular event to corresponding to the zero offset event. Likewise, you also want to bring this event here corresponding to the zero offset event. Likewise, all the events that are coming in your reflection data should correspond to the zero offset distance. And then finally, when entire hyperbola will become flatter, then what you will observe, instead of having this hyperbola, your event will be having a flat line. And then when you will stack them together, then we will be having a better signal to noise ratio. When I am saying stacking, that means you are taking the average of all the events that are coming into your reflection hyperbola. So basically, in the case of normal move out, the variation of travel time with offset is stated in terms of normal move out. Difference in the travel time at an offset and zero offset is given by. So you are taking the difference between the travel time that arrives at a particular offset with respect to the zero offset, and that is the amount that you will have to basically remove into your travel time in order to have your data or the reflection event to be set for the zero offset event. So Tx minus T naught is equal to x square by V naught square plus T naught square to the power under root minus T naught. So you can see that Tx has been replaced by this equation here, and then you have kept minus T naught, that is finding out the normal move out value. Now let's talk about the travel time curve and associated ray path. We are doing this exercise to find out the ray parameter, and if you consider this diagram here, you can see there are two rays associated with the wavefront, and the rays are basically dt time apart. The ray that is reaching to the surface earlier is reaching over here, and another ray is reaching after a dt time at a offset distance of dx. So, or you can say the ray is basically covering the dx distance in a dt amount of time. So if you look at this diagram, then the incident angle is I, that is over here. You can see it is the rays are incidenting at an angle of I, and since the rays are dt time apart, so this ray will travel an amount of v into dt extra distance that it will cover, that is v into dt. And this is, but if you consider this particular triangle over here, this is a right angle triangle, then the sin I value will be v dt by dx. And if you rewrite it, then sin I by v will be equal to dt by dx. So sin I by v is nothing but your ray parameter. I have told you in the previous class that for the flat earth model, you can consider the radial distance to be equal, and those can be cancelled out. So ray parameter that you will remain with will be equal to sin I by v. So the ray parameter is equal to sin I by v, and that is further equal to dt by dx, that is the slope of the travel time curve. So the ray parameter and the angle of distance incidence of the ray emerging at a distance x can be found by dt by dx, the slope of travel time curve evaluated at x. Now we can extend this idea for the case of multiple horizontal layers. So for multiple layer reflections, you can see there we are showing just a 3-layer case. We are just showing a 3-layer case here. So if we extend it for the n number of layers, then the reflection, that is Rn plus 1 from the top of the n plus 1th layer. So, or you can say the bottom of the nth layer, since because we are starting from 0, has traveled through n layers, each of having thickness hj. J is basically varying from 0 to n. The velocity vj. So each of the layer is having their velocities varying from h naught to hn and v naught to vn. As the ray parameter is constant along the ray, since we have said as per our Snell's law, the ray parameter remains constant along the entire path of the ray. So if you consider the case in the first layer and relate it to the jth layer, then what you will see, since the single ray is traveling from the first layer to the jth layer, so the ray parameter should remain constant. So P will be equal to sine ij by Vj, that will be equal to sine I naught by V naught. So a downgoing ray which travels its horizontal distance xj in the jth layer spends the time delta tj in the layer. Thus, in going down and up again, the ray travels a total horizontal distance, that is xp, that means the distance as a function of ray parameter, and that is basically nothing but the total horizontal distance. So basically if you look at this diagram here, this is your receiver and there you have your source. The ray is going down and then refracting into the layer and then going into the other layer and then reflecting back and traveling the path and coming to the receiver. So if you consider this particular triangle here, then what you will see, that is the thickness of the layer, and the distance that is this traveling in this particular layer is x1, or you can say xj if it is your jth layer, and this angle of incidence or angle of reflection, you may say, in this particular layer is the I1. So so you can see that if you consider this particular xp, that means the total horizontal distance, that can be written as two-way travel, because in each layer the ray is traveling twice up and down. So that means it can be twice of summation of j is equal to 1 to n, xj is equal to 2 summation j naught, j is equal to 0 to n hj tan ij. Because if you look at this diagram, tan ij will be equal to xi by hi. So xi, that means the distance traveled by the ray in the jth layer, will be equal to hi tan ij. Since the ray is going down and up, that means twice the distance. So the total distance that it will cover in this particular layer, in the jth layer, will be 2 into hi tan ij, or you can say tan hj, 2 hj tan ij. So xp will be 2 summation for each layer, j is equal to 0 to n hj tan ij, and total time will be the time traveled by ray in each of the layer for upgoing and the downgoing direction, and it will be summed over all the layers. That means 2 into summation j is equal to 0 to n delta tj, that is the time in each of the layer that the ray is spending in going up and down. And if you look at this diagram again, then cos ij will be equal to hj divided by V1 delta T, or you can say Vj delta Tj. So delta Tj will be equal to Hj by Vj into cos Ij. So this is what it is written. So this is the time that you can calculate. So this is what it is written here. So 2 into Hj by cos Ij, and it should be multiplied by Vj as well here. Okay, this will be your total time. So for single layer, so if we suppose these are the things for the n number of layers here. So for single layer, total time yields Tx is equal to 2 in bracket x by 2 whole square plus h naught square to the power under root by v naught. So for single layer, let's suppose this is your single layer here, and here you have a source, here you have your receiver. Let's make it similar to the one that we have seen in the previous slide. That is your source, and this is your receiver here. So for single layer, it will go down and will be reflected at the interface and will be recorded at the receiver, and this is the angle at which it will be incidenting, I, let's suppose, or in case since it is your n is equal to 0, so it will be your I naught. And if we consider cos I naught, that will be equal to, if suppose the thickness of the layer is h naught and the offset distance is, let's suppose, x, so this distance will be your x by 2. So cos I naught will be equal to h naught divided by under root h naught square plus x by 2 whole square. Okay, so if you want to calculate Tx, then it will be nothing but the total distance traveled, that is total distance, that means 2 under root h naught square plus x by 2 whole square divided by the velocity, that is v naught. So this is what it is written here, and cos I will be equal to this one. Now if you want to see for multiple layers the travel time curve for reflection of Rn plus 1 of the top of the n plus 1th layer as hyperbola. So if you want to extend it, the similar thing for the n number of layers, or you may want to see how much time the ray is taking from the reflection of the top of the n plus 1th layer, then the formula will be like this: Tx square n plus 1 is equal to x square by v dash n square plus tn square, where vn is little tricky to find out, or you can say we need some complex calculations to find this velocity, that is the average velocity of the ray that it travels from going from the n is equal to 0 layer to the top of the n plus 1th layer, and this is the Tn is the total time. So Tn is the total two-way up and down vertical travel time at 0 offset. So it is, which is twice the sum of the one-way vertical travel time delta Tj for each layer. Okay, so it is the two-way travel time when there is a 0 offset. So it is basically the total time for the ray which is going up and down for covering the total thickness from the top of the 0th layer to the top of the n plus 1th layer. Now this is the Tn time, that is 2 into j is equal to 0 to n delta Tj, that is equal to 2 summation j is equal to 0 to n hj by vj. So hj is the thickness of each of the jth layer, vj is the velocity in the jth layer. If you want to find out the distance traveled by the ray in the jth layer, that can be calculated by taking the product of the velocity multiplied by time it takes in each of the layer. So that can further be calculated by vj dash by v naught delta tj sine I naught. So If you want to calculate the total distance covered by the ray in all the layers, that will be 2 summation j is equal to 0 to n xj, that is 2 into sin I naught by V naught summation j is equal to 0 to n V naught is Vj square delta Tj. So basically what it is being done, if you look at this particular formula here, that means this is the total horizontal distance, and this formula is being used over here to find out this particular term. And then if you want to find out the ray parameter, that is dt by dx, that is equal to sin I naught by V naught, that is x by say 2 summation j is equal to 0 to n Vj square delta Tj, that is delta T by dt, that is ray parameter, that can be written x upon Vn square T. So we can define V naught Vn square is equal to 2 summation over j is equal to 0 to n Vj square delta Tj by T. So now for vertical incidence, we can say that delta Tj is equal to delta Tj, and that will be equal to 2 summation over j is equal to 0 to n delta Tj, and this Vn square will come out to be this one, and which means that Vn, the appropriate average velocity for the travel time curve, is the time weighted root mean square, or the RMS velocity for the first n layers. So this is the average velocity for the n number of layers, or you can say the RMS root mean square velocity for all the layers. So but the question is, how can we find the each layer velocity or the interval velocity? That we can do it using the disk equation. So let's suppose the reflection is happening from the top of the nth layer, and the vertical two-way travel time Tn minus 1, and the RMS velocity is Vn minus 1. And if suppose the reflection is happening from the top of the n plus 1th layer with vertical two-way travel time Tn and the RMS velocity Vn, then the velocity in the nth layer you can find out using the disk equation. So this disk equation, Vn square is the interval velocity, that is basically the RMS velocity for the nth layer square to the two-way travel time from the top of the n plus 1th layer. Let me say it again. This Vn square, where the Vn is the interval velocity, that will be equal to the Vn square, that is the velocity for the n number of layers, RMS velocity, and this is Tn, that is vertical two-way travel time from the top of the n plus 1th layer, minus vertical velocity or the RMS velocity for the top of the nth layer, multiplied with the two-way travel time, vertical travel time for the n number of layers from the top of the n number of layers, divided by the Tn minus 1. The relationship is called the Dix equation. The resulting velocity is called an interval velocity and is better determined for the larger offset where the slope of the travel time curve is greater. So if we go to the summary of today's lecture, we have seen the study is using the reflected arrival times to determine the velocities within the thrust. So it has wide application in the oil and gas industry, and can be used to find out various other parameters as well, and it is known as reflection seismology. Travel time curve for the reflected arrival is hyperbola. For one layer, it can be this one, which is hyperbola. Travel time curve for n layer geometry is Tx n plus 1 square is equal to x square by v dash n square plus Tn square. Relation between ray path and the travel time curve is P is equal to sin I by V is equal to dt by dx, ray parameter. Root mean square and the interval velocity can be found out using the Dix equation and this particular formula. So that is all for today, and we are going to meet to have larger view of reflection seismology in the next lecture. These are the references. Thank you so much. Bye-bye.